In this video, we'll be reviewing the buckling of columns. So what are columns? Columns are long structures which are generally subject to axial and compressive loads. Axial loads are loads that are applied along the axis. Compressive load compresses the structure from opposite directions. Now, buckling is a phenomenon that's associated with the columns. So that means the beams, when it is subject to compressive force, it tends to bend, and that bending is what we call as buckling. But there could be a scenario where the buckling may be extremely large or is significantly higher. Buckling itself is slightly larger than a lot of other strains or deformations that we generally encounter in solid mechanics. So buckling already is a higher number as far as deformation itself is concerned, but sometimes the deflection may be too high or too large that it may lead to catastrophic failure. We could see that in case of buckling, a small increase in compression force would result in a large deflection. So that means it's not as expected, or it's not even something that we anticipate. As if you consider most of the other structures that we encounter, like beams or like axial deforming structures, buckling has something unique. That means when the force is increased beyond a certain threshold, it tends to show abnormally high deflection or buckling. But as soon as the force is released, the structure comes back to its original shape. So what is happening with buckling? Is it a material failure? Most often than not, buckling is not a material failure, which means the material does not undergo any fracture and so on. It could, but most often it doesn't. That means buckling is a failure which happens before the fracture. It happens even before the yield point. That means buckling is a failure phenomena. We can call it as a failure because the structure failed. It's a failure phenomena which is happening within the elastic limit. That means we are not talking about high amounts of stresses here. We are talking about stresses within the elastic limit when the material is able to return to its original shape. Still the material fails. So what kind of failure is that? So it is what we term as a stability failure. That means the column, the structure is no longer stable to withstand the load, and it moves or transitions from a stable state to an unstable state. So let's take a look at three scenarios which explains the concept of equilibrium. In the case of number one, the left-hand figure, we call it a stable equilibrium, where there's a sphere inside a cylindrical or circular surface, and if you displace the sphere by a small amount, it returns back to its center position. We term this as the stable equilibrium. Any displacement or a small effect, it only produces a small consequence. So the action and the effect are more or less in sync. However, on the two figures, the middle figure and the right hand side figure, we could see that a small deflection could lead to relatively higher amounts of displacement. When the sphere in the center figure is displaced, it tends to topple over. It cannot come back to its equilibrium position. That means what we term this is called an unstable equilibrium. In case of unstable equilibrium, a small action results in a large consequence, and we call this as a catastrophic failure. In case of neutral equilibrium, even though the sphere is displaced, it cannot come back to its previous position. However, it is still in its equilibrium in that position. So what we are more concerned here is the center figure, which is the unstable equilibrium. And that's what happens when the column tends to fail. So coming back to the columns, we are talking about the stability. If you assume the column to be a structure which has a spring, this is again an imaginary scenario. If you consider the spring to be rotational, when it is subject to an external load of P, which is a compressive load, we could see that the the force causes the spring to rotate, and since the material has a Young's modulus or a stiffness of a K, so let's consider the structure to be displaced to the right side, as we can see here at point B. What we can see here is anytime the load increases, the structure tends to deflect. However, there is a restoring moment. There is a force or a moment that opposes this applied force, the bending moment, which causes the structure to come back. So if you remove the force P, the structure comes back to its original position. So you could keep increasing P, and the restoring moment always causes the structure to return back. So the applied moment, we call it as the upsetting moment, and the moment that brings it back, we call it as a restoring moment. So it's a matter of equilibrium, just like the previous case where we saw the displacement of spheres from its equilibrium position. In this case, we are talking about two opposing moments, the upsetting moment and the restoring moment. Now the question here is, what causes failure? It's failure could happen when the applied load exceeds a critical point or the critical load. At this critical point, what happens would be the two moments, the upsetting moment and the restoring moment would be equal. Above that, the upsetting moment would be higher. That causes the structure to fail. So why is critical load important? Critical load is also termed as P sub CR, which refers to the magnitude of the load at which the two moments, the restoring moment and the upsetting moment, are equal. So once we determine the critical load, we could see that the critical load is related to the length of the structure as well as the spring constant, which is a K. As far as the critical load or the critical buckling load is concerned, so that's the point where the two moments are equal. If you try to increase the load, the column fails. So that's the significance of the critical buckling load. And most importantly, we could see there are two factors. There was a K as well as a L. The L factor is the length, which means if you increase the length of the column, the critical load value decreases. That means your load carrying capacity of the column would significantly decrease, which is natural. If you think about a long, slender structure and you apply a load, it tends to deflect a lot more than a thicker structure, right? And a shorter structure. So always the length of the column has a significant bearing on its critical load. Most importantly, as I mentioned before, the failure happens at low stress values. That means within the elastic limit lesser than the proportionality limit, which is a concern because most engineering structures, we often consider the failure as a yield point or the ultimate tensile strength. And in case of columns, it happens much earlier than those failure points. That means this is not a material failure, rather it's a structural failure. We call it as a stability failure.